this tutorial is about a tool. It's about the cluster expansion, which turns out to be a very old tool from statistical physics. But somehow my goal here is to tell you about this tool and hope actually that you come up with your own applications for using it once you've learned about it. So I have been like thinking about this and using this for maybe 4 years, 5 years now. But I'm still discovering places where it's relevant. And so I really hope that especially this audience will come up with some new applications. So, you know, I've written some papers about this with Tyler Helmuth, Bruce Rex, Matthew Jensen, Peter Kibosh, Sarah Cannon, Aditya Padakuchi, and others. So this is all based on stuff I learned from doing work with them. And so what I want to do over the course of the 2 lectures is first to sort of set up the setting. The setting will be spin models on graphs, which is pretty closely related to what Quickly talked about this morning. I want to sort of advertise how important the normalizing constant is. So the partition function, and sort of say, if you understand this, you understand a ton about probabilistic algorithmic questions. Then I'll talk about what is the cluster expansion.
Sorry, Will, sorry to interrupt. We're supposed to record you.
Let me say one sentence beforehand, just so you get situated and you can, have your favorite problem in the back of your mind. But a lot of times we're dealing with probability distributions over lots of random variables, and sometimes we're in a setting where we think these random variables are close to being independent, but not independent. Okay? And the simplest way to describe what the cluster expansion is, it's a way to really precisely quantify and give formulas for quantities when you're close to being independent but not. And so if you have that in the back of your mind, I think it will help. Good. And please do interrupt, ask questions, have me explain what the writing on the board is if you can't read my handwriting. Okay, so the setting. The setting will be spin models on graphs, or you could even think spin models on hypergraphs. And we'll focus on 2 main examples. And actually both, quickly mentioned both earlier, but let's define them. So the first is the easing model. Okay, so the easing model is a probability distribution on cuts of a graph. And we'll sort of encode a cut by ±1 assignments to the vertices of the graph. And so, here are sigmas in ±1 to the v of g, the vertices. And the probability you pick a particular cut is e to the, let's say, beta sum over edges, uv is an edge, sigma u, sigma p. Okay, so we're looking over all the edges, and we're giving a +1 in the exponent if the spins agree, because it's 1, 1, or -1, -1, and a minus if they disagree. And we have this parameter beta in front of everything. Now this is not a probability distribution, you have to normalize. And we will always call this normalizing constant z, and it's the partition function. And what is z? Z is just the sum over all sigma. So this is the easing model. If beta is positive, then you prefer to see the same spin across an edge. Okay. Good. That's one model we'll talk about, and the other is the hardcore model, which we introduced. So let's be precise. Hardcore model is a probability distribution on independent sets of a graph. And what's the probability you pick an independent set? So mu of I is lambda to the size of I divided by the normalizing constant. The normalizing constant, this you maybe have seen. This is the independence polynomial of the graph G. Okay, so these are the two models we'll mainly focus on. And what kind of questions can we ask about these distributions? It depends on where you're coming from. And so, I want to give a perspective from some different fields. So Any questions? So one question is, what does a sample from mu look like? Can we sample efficiently? Maybe can we compute or approximate this normalizing constant? Okay, so these are some questions you might ask, and it depends on what field you're in, sort of what the setting looks like. So,
Well, sorry to interrupt you again. There's a switch on there that you turn on your mic.
The technology.
great, now I see the light.
Oh, awesome. All right.
Okay, good.
As long as you're interrupting, can you put the mic actually on the top of your head?
Sorry to say that.
Now it'll be super awesome and we'll never talk to you again.
But I want you to ask questions, but
Okay,
just,
but they're
just
not
not
together.
technological ones. Okay, good. So statistical physics, what are the questions like? The questions here, we're going to, they would study these models on lattices, like ZD, and ask about phase transitions. We'll talk about this. In algorithms, so this is what Kwikwi talked about. We want to efficiently compute these things or sample. That's one field. Combinatorics, what does this have to do with combinatorics? Well, this Z is a generalization of counting. Okay, so in particular, let's say plug in lambda equals 1 to this hardcore partition function. You just count the number of independent sets in a graph. And somehow, actually, this is a really central problem in combinatorics, counting independent sets in a graph or hypergraph. And then I'll throw in a fourth one in probability theory. So actually, partition functions are very closely related to studying large deviations. Okay, and somehow large deviation probabilities are very, very similar to computing partition functions. Good. So that's somehow the setting. Let's get some intuition first. So some intuition. And here the intuition will be from statistical physics. So I want to think about the Ising model on, let's say, ZD, but with periodic boundary conditions. So the discrete torus. Okay, so you have, let's say, Z2. You have this integer lattice, and then we just say that the sides are identified. So you have a nice graph, and we're thinking here, 2, D is 2, and that's fixed, and we're thinking bigger and bigger graphs. Okay, and now we want to think about what does this probability distribution that I defined here, what does it look like? Okay, let's do some easy cases first. So beta equals 0. If I take beta equals 0 and look at the Ising model on this graph, what is it? Uniform, yeah, to be a bit more precise. So I have plus minus 1s on all the vertices, but how do I choose them? Yeah, so they're just IID, probably 1/2 plus minus 1 spins. So that's very easy. What if I take beta to be plus infinity? Okay, so now I really, really care about having the same spins across vertices. Well, now you're just going to flip a 50-50 coin, and do everyone the same, either all plus or all minus. Okay? And we can also talk about hardcore on ZD. This one's a little bit different. So lambda equals 0. Well, if lambda is 0, then you just, with probability 1, you pick the empty independent set. That's very easy. If lambda is infinity, now I have to be a tiny bit careful here, right? Let's say the side length is even. Then you want to pick a maximum independent set. And on Z2, there's 2 maximum independent sets. There's the all evens and the all odds. So again, you're going to flip a coin and either have all evens or all odds. OK, so those are easy. But here's the question of statistical physics. The question is when beta or lambda are small but positive, does mu, and let's say mu or z, resemble the easy beta equals 0 or lambda equals 0 case? And conversely, when beta or lambda is large but finite, do mu and z resemble the easy beta equals infinity, lambda equals infinity case? Okay, so we somehow have a very simple picture in the 2 extremes. And then the question of statistical physics is when you push in from those extremes, does the probability distribution you get, or does the partition function, can we understand it as a perturbation around these easy cases? Okay, so resemble, is it a small perturbation? Okay, and I'm not going to define phase transition today or anything like that, but a phase transition does occur in both of these models on Z2, on ZD, where qualitatively, in a lot of ways that can be made precise, for small lambda, you resemble the empty or the independent case, and for large lambda, you resemble the all plus or all minus or all even, all odd. So that's the question in statistical physics. And even more, so getting closer to the topic of the lectures, we don't want to know just that it is a perturbation. We want to compute the perturbation. Okay? So what does it mean to compute the perturbation? Well, one thing would be to compute the partition function. It's very easy to compute the partition function in these examples, but we might want to compute it in the intermediate regime. What does it mean to compute the perturbation for the probability measure? Well, maybe it means like computing all the moments or the joint moments or anything you might want to compute about a probability distribution. So that's the goal. Good. So that's the intuition. And just a quick remark about this intuition. Notice that I've talked about perturbing from at least 3 different places. I talked about perturbing from an IID system. I talked about perturbing from an empty system. And then I talked about perturbing from like an optimal solution to an optimization problem. Okay? And the nice thing about the cluster expansion is that it's flexible enough to compute perturbations from any kind of simple state like this. And we'll see this as we go. Good. OK, so the next thing I want to talk about is why is the partition function so important? Or in other words, I basically want to reduce both of these problems to one problem. Computing perturbations around some state, I just want to say we really just care about computing z, the partition function. Okay, so I'll give a little bit of a pitch for why this is important. So let's write, for the Ising model, let's write h of sigma is this thing in the exponent. So sum over uv edge, sigma u, sigma v. So what is this really? This is the number of monochromatic edges under this coloring minus the number of bichromatic edges. Okay, and if you pick sigma from the Ising model, this is a random variable. Okay, pick the random sigma, evaluate this function. And this is maybe something you would want to understand. So we can ask, can we compute moments of this particular function h? So let's do that. Let's look at, how about expectation of h? Well, let's just write the definition. Sum over all sigma, h of sigma, mu of sigma. Well, this is sum over sigma, h of sigma, e to the beta h of sigma over z, right? Now you can, so z of beta. You can pull the 1 over z out. That's just a constant. And then you have the sum over sigma, h of sigma, e to the beta h of sigma. That's a derivative. Okay? So this is z prime of beta over z of beta, which is just log z of beta prime. No, I don't think so. Beta is the variable.
Oh, would you take the
Yeah.
derivative?
Yeah. So you're actually completely right if I was doing it for hardcore. So there would be an extra lambda.
Yes.
Yeah, good. Good. Thanks for asking. Okay, so the expectation is just the derivative of the log partition function. Okay, you can do it. You can take another derivative, right? So you can say log z of beta. Okay, so I think I'll leave this as an exercise, but maybe someone wants to shout out the answer. So if you take two derivatives of the log partition function, so you can start to think what happens, right? If you take another derivative, you get this. So guess what this is? The variance, good. So this is exactly the variance. So this is the variance of h. And so then what is, let's say, so what is the kth derivative of the log partition function? Aha, I was trying to trick you, and you fell for it. Good. It's not the kth moment, no. Yeah, the kth cumulant. So it turns out in this world, instead of moments, actually something called cumulants are extremely important. And so let me define what they are, because they do come up a lot. Thank you for falling for the trick. Good. So what is the cumulant? So I'll write what this is, kappa k of h. But I have to define what the kth cumulant is. So for any random variable, okay, let's say that has a convergent moment generating function, you have, let's say, kx of t is log expectation e to the tx. So this function is called the cumulant generating function. All it is the, it's the logarithm of the moment generating function. Okay? And then what we can do is we can Taylor expand this around t equals 0. So kx of t is sum k equals 1 to infinity t to the k over k factorial times some coefficients. And the coefficients are the cumulants. So that's one way to define cumulants. What's nice about cumulants? They're just like a different basis of the moments. Okay, so they're linear combinations of moments. They have some nice properties. So if k is at least 2, then kappa k of x plus constant is kappa k of x. let's say x is Gaussian if and only if kappa k of x is 0 for all k at least 3. Okay, so the first cumulant's the mean, the second is the variance, the third and higher are the higher cumulants. But you have a Gaussian random variable if and only if your higher cumulants vanish. Okay, and so one way to prove convergence to a normal distribution is to show that the higher cumulants tend to 0. Okay, a Poisson random variable, all the cumulants are lambda. That's another nice one. But it's very natural in this setting. The cumulants are just derivatives of the log partition function. Good. Let me just say, the way I've defined the hardcore model, it's not as an exponential of some function. It's lambda to some power. So if you do the derivative, it's slightly different. So here, I'll just write this because we'll need it later. But in the hardcore model, if you look at the expected size of the independent set, this is lambda times the first derivative of the log partition function. Good. Let me also say you can do a bit more. So what if you wanted to look at the characteristic function of H? Okay. Good. So if you want to understand a random variable, another thing you might want to compute is like the characteristic function, right? Expectation e to the itx, or ith in this case, where I is the complex I. What is this? Well, this is kind of nice, right? This is z of beta what do I want to say? Beta plus it over z of beta. Okay, so you can do that. Check as an exercise that this is correct. Hopefully that's correct. But the point is that something like a characteristic function or a moment generating function is just the ratio of two different evaluations of the partition function. And so if you understand this partition function, you're doing a great job understanding the model. Okay, and even more. So the other thing is, it's a very useful generalization to actually, instead of thinking of one parameter, beta or lambda, to make this multivariate. Okay, I'll do it for hardcore. So now we have a vector lambda from vertices to, okay, let's say complex numbers. You can think of it as positive real numbers. And now what is the partition function? Well, this is the sum over independent sets. But now instead of lambda to the size, you want to multiply over all the vertices in your independent set this particular activity at the independent set. Okay, and that's perfectly fine. And now you can define, you can have, let's say, xv, this collection of random variables. These are the indicators that the vertices are in the independent set. Okay, so now you have a vector of random variables. And if we wanted to understand a single random variable via its cumulants, now you can ask to understand collections of random variables via their joint cumulants. Okay, so kappa, let's say, x1 to xk. This is the joint cumulant of x1 up to xk. This is the coefficient of T1 times Tk in the Taylor series for log of expectation e to the, and now it's t1 x1 plus t2 x2 plus tk xk. Okay? And so in particular, you can say something like, what if you look at like lambda v times the partial derivative of log z of your vector lambda with respect to lambda v. Okay, so now you have this vector of lambda, and you're only taking the derivative with respect to one of them. What do you think you get? So before, when we differentiated with respect to lambda uniformly, we got the expected size of the independent set. So now what are we going to get? Yes, good. So this is expectation of xv, which is the probability v is in the independent set. So in Quiqui's language, this is the marginal probability in the full measure of v. You can do more, right? So if you look at lambda u, lambda v, so now you take two partials, partial lambda v, partial lambda u. What do you get? Well, you get the covariance of xu and xv. Okay. And then you can do higher and higher derivatives and get more complicated correlation type things. But the point is, if these random variables were 0, then, if they were independent, you would get 0. And so this is some measure of dependence. And so one way to phrase one of the statistical physics questions is, in your model, does like the absolute value of kappa xu xv, something like this, does this go to 0 as the distance between u and v goes to infinity? And now if you think back to like the intuition, it really depends on which regime you're in, right? So if we said that like in this large beta regime, we're going to flip a coin and decide if we're going to be mostly plus or mostly minus, right? And then you're going to see mostly pluses or mostly minuses, then definitely this will not decay, right? Because you're going once you know that 1 is a plus, it makes it likely that something very, very far away is also a plus. And same with hardcore. If you know that an even 1 is occupied, it's going to make it much more likely that an even 1 even far away is occupied. But we can hope that if we're in the other regime where lambda and beta are small, that we can show something like this. Okay, and cluster expansion will allow us to do this. Good. Okay, so that's the setup. That's our setting and why we care about the partition function. So questions before I go on? Yeah.
So in Quiqui's talk, I mean, in order to get bounds for the spectral independence, you have to worry about, all conditionings too.
Yes.
Is there any convenient way to get this kind of information from the partition function, or not really?
I mean, you can
just specialize it, but I'm just wondering if.
Yeah, you can specialize. So like when you condition, you get a new partition function, and then you can take the derivatives. So it all works. And for a lot of these models, they have the nice property that when you condition, you get a new instance of the model. Yeah, so that's right. There will be some divergence, though, because Quiqui was really talking about how do you get the best possible bound. And what we're going to talk about, you get a lot of information, but it's not going to hold in the biggest possible regime. But good. OK, so what is the cluster expansion? So I'll tell you what it is, and then I'll sort of give some history, and then I'll give some examples, and then I'll be more precise. But what is the cluster expansion? It is the, let's say, multivariate or univariate, Taylor expansion of log z of beta, log z of lambda around 0. Okay, so I guess, yeah. So really what it is a multivariate Taylor series. That's all it is. And I'll tell you what the coefficients are, and they have some nice combinatorial meaning. The history is that this was first studied by Meyer in statistical physics in the 1940s. And then, when you talk about power series, of course, it's incredibly important if it converges or not. And so really the first rigorous study of convergence was done in the 1960s by Grunwald, Penrose, Ruel. Okay, again in statistical physics. And since then, lots and lots of interesting stuff has come from this. A little more history is that somehow it came into combinatorics, and I'll tell you the connection. In the 1980s, with a really nice paper of Shearer, and then Scott and Sokol looked at this. And then something very closely related, basically the same thing, studied in algorithms, starting with Barvinack. So he calls it polynomial interpolation, but it really is about cluster expansion. Okay, so why was Meyer interested in this expansion? He was interested in understanding the equation of state. Of a gas. So equation of state just means some equation relating the things that you can measure about, let's say, a gas or a fluid. So pressure and density. How do these relate? Pressure, density, temperature, things like that. Do you have an equation where they're related? And that's what he was interested in. He was interested, how do you determine the equation of state of a gas? And I'll give sort of a simple example. To start. So the first thing is that there's something called an ideal gas where the gas molecules don't interact at all. Okay, and so let's talk about a discrete ideal gas. So what would a gas that doesn't interact at all? Well, this is just going to be like the hardcore model. So these are possible sites for gas molecules, but there's going to be no edges. It's just going to be an empty graph on n vertices. Okay, so that's my discrete ideal gas. It's basically IID occupation with probability lambda over 1 plus lambda. Okay, so now let's compute the equation of state. It turns out, what's the pressure? The pressure in physics is the limit as n goes to infinity, 1 over n. N is the number of vertices, log of the partition function. This is what they call the pressure. Now, in this case, it's very easy for us to calculate this. So there's no interactions. And so each of the vertices can be n or out. If it's n, you get a factor 1. If it's out, you get a factor n, you get a factor lambda. Out, you get a factor 1. So it's 1 plus lambda to the n is the partition function. Now you take a log and divide by n. Well, you get log of 1 plus lambda. And this is the pressure. So we'll call this P of lambda. And then the other thing you could talk about is the density. What's the density? Limit as n goes to infinity, 1 over n, expected number of particles, so expected size of our independent set. Again, this is very easy because everything's linearity of expectation. You know the probability this one's occupied. This is lambda over 1 plus lambda, and this we'll call rho. Rho is the density. And so what's the equation of state? We want to relate the pressure and density. So if you solve for this, you get that the pressure equals log of 1 over 1 minus rho. Okay. Now, if you imagine that rho is small, then to first order, this is P equals rho, which is the same as PV equals nRT. So maybe you remember that from high school, right? So, N over V, that's the density. Temperature we don't have in this, R is a constant, and so you get pressure equals density. And to first order, this is what this is. Okay, so the cluster expansion, the way we're going to define it is a way to take a gas that's interacting, weakly interacting, and measure the corrections to this equation of state. Okay, so what does it mean to weakly interact?
So
Yeah.
why is that the pressure? I mean, like, where did that come from?
I think it actually is the pressure. So if you think about like how much the particles are hitting the boundary of a box, if you measure that in the right way, this actually will measure that. That's my extent of physics knowledge, though. But I think it really does correspond to what you would think of as pressure.
Like 1 over n log z, you're saying?
Yeah. Yeah.
But what does it mean for these particles to be independently of, like this location to be independently occupied?
I mean, in this case, it just means that I have a set of locations that I number 1 up to n and IID flip things. In the continuum, if you were thinking of a gas in a room, it would be that your gas is a Poisson process. That's the ideal gas in a continuum. So Poisson process is non-interacting points. And if you do the same thing with Poisson process, you will literally get P equals rho.
So the physics feature for like computing pressure and stuff, like there are particles that are moving around, perhaps hitting each other, but hopefully not hitting, and then they hit the boundary sometimes. Well, how do you, like, are these locations there, basically, like, is the measure you're defining there, like, the probability, like, if I look at this process of the,
I mean, not in the discrete case, right? Because there's nothing moving around here. But what you would want to look at is like how the partition function changes when you add one more layer. That would somehow measure something like that. Okay, good. So so let's continue. So that's the goal now, is to come up with some way to explicitly compute deviations from this ideal gas law when you have weak interactions. And what I'm about to tell you is very important. What does weak interactions mean? Well, weak interactions could mean that there's few edges. Okay? The fewer edges, the fewer interactions you have. But it could also mean if you fix the graph, the smaller lambda is, the less the interactions matter. So weak interaction is both small degree and small lambda. And there's some way in which these cooperate. Okay, so that's important. Good. Okay, so now I really want to tell you what cluster expansion is. And so the setup will be something a bit more general, and this will be something called polymer models. And there's a short, very nice paper by Katetsky and Price where they sort of introduce this in an abstract way and talk about cluster expansion and convergence. But it's nice to think about. So what's the setup? We have a set of polymers. So our set will be called C. And what you should think about, because I think every example will have, you should think of polymers as some connected subgraphs of some host graph. Okay, so think of some big graph, and polymers are some geometric connected subgraphs in this host graph. Okay, so you have your set of polymers. Each polymer has a weight. Okay, and let's say this is a complex number. You can think of it as a positive number, but it's a complex number. And we have an incompatibility relation. So we say that gamma and gamma prime can be incompatible with each other. And we want it to be symmetric and reflexive. In particular, so gamma always has to be incompatible with gamma, with itself. And if you're thinking of subgraphs, just think of two things being incompatible if the union is also connected. So if they're touching. Okay, so that's the setup. You have some abstract set of objects. Each one has a number associated to it, and there's some relation between them when they're compatible. And just from this, we can define a partition function. So this is the polymer model partition function. You sum over pairwise compatible subsets of polymers, product over gamma, weight gamma. Okay. Good. So that's the polymer model partition function, and it's in this model that we'll talk about cluster expansion. Let me give you a couple examples of polymer models. Okay, so the example number one, and this is somehow the template, is if you have some graph and your set of polymers is just your set of vertices, and the weight of a vertex or weight of a polymer is just lambda. And then we say V and U, V and W are incompatible if the distance between V and W is at most 1. So if they're neighbors or if they're the same. So then what is the polymer model partition function? So what are we doing? We're summing over collections of vertices that are at pairwise distance at least 2, lambda to the number that we took. So this is just the hardcore partition function. So this is a generalization of the independence polynomial. In fact, I could have put lambda v, and it would have been exactly my other model. So in a sense, I haven't really done anything. I just redefined this multivariate independence polynomial and called it something else. There's a reason somehow to do this. Example 2, now this is going to get a little more interesting. Example 2, let's take the Ising model again. Okay, so let's write the partition function of the Ising model. Sum over sigma e to the, let's write it like product over uv edge e to the beta sigma u sigma v. Okay, so that now just to avoid trigonometric functions, does anyone like trigonometric functions? No, no one likes that. If beta is small, e to the beta is like 1 plus beta, right? So let's just write that. That's just a change of variables. So let's write 1 plus beta sigma u sigma v. Okay? So now I have this sum, a product over edges, this 1 plus thing. So there's a nice trick you can do, and you can rewrite this as a sum over subgraphs. So this is sum over sigma, sum over f, a subgraph of E. Well, you're going to get a beta for every edge, and then you'll get a product over E, uv in f, sigma u, sigma v. Okay. So I'm just expanding the product. Okay, that's cool. Now I can reverse order of summation, right? I can switch the order here. So this is sum over f. Now I have beta to the size of f. Sum over sigma, product over the edges, sigma u, sigma v. Okay, now that's getting a little bit interesting. So imagine f has a vertex of degree 1. So you look at the edges, the graph that's defined by the edges of f, and there's a vertex there. Well, it's going to have whatever you do, it's going to have the thing where u gets 1 and the thing where u gets -1. And so it cancels. And that's actually true if you have any odd degree vertex. So the only f's that survive this are even subgraphs. So edges f, where the subgraph they form has all even degrees. So we can, and then if they're all even degrees, then this is just a 1. Okay, so this equals sum over f even subgraph beta to the size of f. Okay, that's kind of nice. It's even nicer, right? Because an even subgraph might look like that, right? But if this weight factorizes over the connected components, yeah.
Sum of the sigmas somehow should be some number, or is?
Well, the sigma, remember, the product of sigmas is only 1 or -1, because sigma is +1 -1. Yeah, there might be a 2 to the n. Yeah. Okay, good. Yeah. Yes, good point. But yeah, otherwise it's correct. No, but I mean, that is funny, but like that is something that is easy to understand, a constant that you pull out. Okay, but the point is that this weight factorizes over connected components. And so now I can say that my polymers are connected even subgraphs, right? And then my partition function becomes sum over collections of compatible polymers, product of this beta to the size of gamma. Okay, so we've rewritten the Ising model up to scaling Ising model partition function as a polymer model. And notice that like the weights now are small when beta is small. Oh, the compatibility is good. So 2 polymers are incompatible if their union is connected. So if together they would make another polymer, they should be incompatible. So these are compatible, but like these are not compatible. Good.
What do you mean these are not compatible?
Because they share.
Because their union is connected. I'm saying if this was one polymer and that's one polymer, because that would be its own polymer. Yeah, good. Okay, good. And so already you sort of see that like in this thing that just looks like an independent set model, we can perturb around the empty independent set, but we can also perturb around independence, right, for the Ising model. Good. Let's do another example. Yeah. And notice that like from all sorts of points of view, connected objects are much nicer than not connected sets of objects for like algorithms or anything like that. Good. Okay, actually, let me skip the next example and tell you what the cluster expansion is. So okay, so now we have our setup. We have this polymer model partition function. We want an infinite series for log of that partition function. Okay, so now I have to give you a couple definitions. So one is, what is a cluster? A cluster is a tuple, let's say cluster capital gamma. Maybe I shouldn't use gamma. Cluster capital X. It's a tuple of polymers so that the incompatibility graph h of x is connected. Okay, so what's a cluster? It's maybe gamma 1, gamma 5, gamma 1, gamma 2. That's a 4-tuple ordered polymers. And all I'm insisting is that if you make the graph on these objects, where you put an edge if they're incompatible, so in particular, gamma 1 has to be joined to gamma 1. Okay, maybe gamma 2 is joined to gamma 1, and maybe gamma 5 is joined to gamma 2. So if you put that incompatibility graph on this tuple, it should be connected. That's a cluster. Okay? And then the second definition is a combinatorial thing. The Ursel function, phi of h. So this is a functional on a graph. What is it? It's the sum over all edge subsets of this graph, so that the graph with the vertex set of h and the edge subset a is connected. So it's connected subgraphs, connected spanning subgraphs of your graph, minus 1 to the size of a. And I'm going to put a 1 over v of h factorial here. Okay, so this is some combinatorial function of your graph. It turns out this is an evaluation of the tup polynomial of your graph. Good. Okay, so then I can say, what is the cluster expansion? As a formal power series, log of this polymer model partition function is the sum over clusters, this Ursel function of the incompatibility graph, product over your polymers in your cluster of the weight. Notice that this is definitely an infinite series because I can always take like gamma 1, gamma 1, gamma 1, gamma 1, gamma 1. That's a cluster. So this is definitely an infinite series. And at the moment, this is just a formal power series. We don't know about convergence. Yeah?
What are you summing the Ursel function?
Subset of edges, so that if you look at the original vertex set with that set of edges, you're connected. Yeah. So let's do an example. This is an important but very simple example. And maybe we'll stop after this example. Let's just take our graph to be a single vertex with weight lambda. So what are the clusters? So what are the clusters? If this is my graph, my polymer, I just have one polymer with weight lambda. What are the clusters? Well, you can take any number of copies of that one thing. Okay, so the clusters are 1 copy, 2 copies, 3 copies, and so on. What's the incompatibility graph? Well, it's a clique on that many vertices. So h of x is a clique. Okay. So let's start to do this. So this would say log z. Well, the first one, okay, you just have 1, so you get lambda. Now you have here's your graph. There's only one term in here, that one edge with a minus 1, but you have a 1 over 2 out here. So you get minus 1 over 2 lambda squared. Next, you have a triangle. Triangle's a little bit more complicated, right? You have 3 sets of 2 edges that give you plus 1, so plus 3, minus 1 set of 3 edges, which gives you minus 1. So 2, but divided by 6 for 3 factorial. Who can tell me what's next without computing anything? You already know. Good, yeah. I mean, and so on and so on. But of course, it has to be that, right? Because the partition function is just 1 plus lambda, and so we're just expanding log of 1 plus lambda. Okay, it's just the power series for log 1 plus lambda. But already, like, and we'll end the first lecture here, there's something very important that you see. When does this converge? This converges if lambda is less than 1. In the model itself, picking one point independently with probability lambda over 1 plus lambda, there's nothing special about lambda's 1. The singularity here is at minus 1. And so we're seeing that this method, like something that has nothing to do with the probability distribution, this negative lambda, somehow determines whether this method works or not. Good, okay, let me end there, and then we'll come back and continue. Okay, thanks for coming back. So we'll continue where we left off. So what I told you was, what is the cluster expansion? We gave this setting. We said, what's the cluster expansion? We did like the most simple example. We just took a hardcore model on one vertex, and we saw what we expected, the Taylor series for log 1 plus lambda. Okay, let's continue. Let's be a little bit more ambitious and look at still a hardcore model, what happens. And now I want to say my graph G is just a triangle-free graph on n vertices. And this is going to be an exercise. I won't go through the counting. But what am I expanding here? Well, I'm looking at the Taylor series for log z. But if you think about it, like, what's going to happen? Like, for every vertex, you're going to see the same expansion that you saw for the single vertex graph. And that's sort of represented by this graph we had the ideal gas before, 1 plus lambda to the n. And so one thing we can do is we can just say, well, I know that's going to be there. What are the corrections? And so I could either subtract the cluster expansion for that, or I could just divide by it here. Okay? And so you're not going to see in this expansion any of the clusters corresponding to repetitions of single vertices. That's what we've removed. And then what do you get? Well, okay, the first correction, remember we're looking at for corrections to the ideal gas. The first correction is something to do with edges. Minus lambda squared times the number of edges. Okay, that's good. It should be minus, right? You're killing off independent sets by adding edges. Good. If you come from probabilistic combinatorics, this should sort of look familiar. This is like Janssen's inequality. This is exactly Janssen's inequality. Expected number of violated constraints if you think about putting things in independently and seeing edges. And then, okay, then you're going to get some lambda cubed terms. What are the lambda cubed terms going to consist of? Well, they're going to be connected subgraphs on 3 vertices. I've said there's no triangles, just to make life simpler. So you can get P2s. This is a path on 2 edges. And you're going to get something to do with edges, right? Because you can have an edge and a repeated vertex. So at least it's believable that the next coefficient could involve this. But I'll leave an exercise to verify exactly the coefficients.
So this connection you mentioned to Jensen, this sounds really interesting. So I mean, Jensen gives you actual bounds. So if you truncate the series at some point, do you get actual bounds?
Yeah, we're getting there. Yeah, but like you should really object to what I'm saying because this is just a formal power series. This means nothing if it doesn't converge. Yeah. Yes, so good. Yeah, that's exactly the right question to ask. Did I want to say? Oh, let me actually be a little bit more precise. So, what is this really? This is the probability that a IID lambda over 1 plus lambda subset is an independent set. Okay. So that's exactly what this probability is. It's equality. And so then you can start to see why all this stuff might be connected to large deviations. This is a large deviation event that you see no edges, and now I'm giving some expansion. Good. Yeah, and exactly what Anchor asked, like, what is this? What bounds does this give? So we need to know if it converges. Okay, and so I've conveniently written up one convergence criteria, and this comes from the same paper where Katetsky and Price defined these abstract polymer models. But I'll walk you through this convergence criteria, and then we'll see some small examples. The convergence criteria is in terms of 2 functions, A and B, that map polymers to real numbers. For the moment, just think of A as measuring the size of a polymer. So if our polymer is some weird connected subgraph, call it the number of edges or number of vertices. It's a measure of size. B, just think of something like size, but like it's going to give you like a way to truncate things. So you can imagine B is 0 if you like for the moment, if you're just interested in convergence. And what's the condition? The condition says, look at every polymer in your set, and then some inequality has to hold. What inequality? You have to sum over every single polymer that's incompatible with it, absolute value of its weight, exponential of A of that polymer plus B of that polymer, and that should be at most this size of the original polymer. Okay. And if you have that for every polymer, then the conclusion of this theorem is cluster expansion converges, and we get some truncation bounds. So this is exactly what you're asking. So what does a truncation bound look like? Here here's my actual log partition function. And I'm subtracting the truncated cluster expansion. So I'm going to sum all the clusters whose sum of b values is at most t. So if you imagine b as some measure of size, like this is like all clusters whose sum of sizes are at most t. Then this is at most, okay, now here's something, you should think of this as like number of vertices of your graph. Technically, it should be like you sum over some subsets of polymers that what they're incompatible to covers all the polymers. It's like a cover of the polymers. That sum times e to the minus t. So you get exponential decay in the error bound in where you're truncating this cluster expansion. Okay, and let's look at this. So, what's the trade-off here? One trade-off is somehow the bigger your polymer is, the more things it's going to be incompatible with, right? And then you're summing up these things, and you're hoping that these weights are small to kill off this stuff. Okay, so we'll see some good examples. But any questions about that statement? So, to use the cluster expansion, you need to know it converges. If you want to use it for approximation, either asymptotics or algorithms, you really want explicit error bounds, and this gives that. Okay, so let's do.
Will, I do have a question.
Yeah.
The first question is a boring question.
Good.
How do I spell is that two C's in a row and
K-O-T-E-C-K-Y. And there's some accents. And the second question?
The second question is, okay, again, it's another boring question. So, just because it was a little fast for me. So the second thing, the sum over, is that x in cover?
Yeah, so no, this is sum over gamma in a cover. I just want to say you find some subset of polymers. There might be many, exponentially many polymers in your set, but you just want to find some subset so that every polymer appears once in the incompatibility stuff. So it's like the way you should think of it is like if your polymers are subgraphs of some host graph, this should just be n, number of vertices, because like each vertex, a polymer appears in contains some vertex. So just think of this as n e to the minus t. It'll be more clear, I think.
Wait, so as long as there exists for any cover, this statement holds,
Yes.
Okay.
Yeah, so you want to find a small cover, but usually it's going to be proportional to the volume.
The better the cover, the better the upper bound, I guess.
Yeah, but this thing is really not going to matter. This is going to be linear in the volume, but it's really the exponential that you care about.
Okay, all right.
Yeah. But what this says is if you want really small error, you're going to have to take t to be logarithmic in n to kill off this. Yeah.
Another thing is, where is a in the last expression?
In this expression? Right. This is a of gamma.
That's a. That's okay. And in the other expression, is it what is on the right hand side?
A of gamma.
So this is a.
I'm just summing. We're just summing this equation up.
Okay. A is everywhere.
Yeah. Think of that as size. Okay. So some examples. So let's say G is a max degree delta graph. And now we're just doing hardcore model. So with a single lambda. So again, this was our first example of a polymer model. Polymers are just single vertices, and incompatibilities neighboring or being the same. So what is the condition? So the condition is for all vertices, if you sum over u in the closed neighborhood, so itself and the neighborhood, absolute value of lambda. Okay, let's say A of V is just 1. Everything has size 1, and B is 0. E to the 1 is at most A of V, which is 1. Okay. So A of V is 1 for all V, B is 0. This is the condition. Now you're a max degree delta graph, so there's delta plus 1 things in the sum. And so this is the same as absolute value of lambda times delta plus 1 times E is less than 1, or absolute value of lambda is less than 1 over E times delta plus 1. So cluster expansion for max degree delta graph will converge if lambda's in a disk of 1 over e times delta plus 1. Does this look familiar to anyone? Lovász local lemma. This looks a lot like Lovász local lemma, right? In fact, there's a very precise connection. So, this is an aside, but incredibly interesting. So Shearer, he has a paper called On a Problem of Spencer. And what he proved was an optimal bound in this setting. You just have max degree delta graph, uniform lambda. What's the optimal bound here? And he got some expression involving deltas that's asymptotic to 1 over e delta. And then he also showed that if I give you a dependency graph and then say what's the best probability bound that you can apply the Lovász local lemma to, it is exactly the nearest 0 in the partition function of the independence polynomial of this dependency graph. So convergence of cluster expansion is directly related to Lovász local lemma, but for negative lambda, which is kind of interesting. So not the probabilistic side of the hardcore model. But that's an aside. The Shearer's paper is like 4 pages, and it takes like 4 weeks to read. There's also like a 100-page paper by Scott and Sokol that expound upon this relation in great detail. Very, very interesting and recommended. But this is like sort of a different connection than we're interested in today. We're interested in the positive lambda, counting, algorithms, sampling. Good. Let's quickly just check Kotetzky price condition for our Ising model expansion. So I rewrote this. Remember what our expansion was. Polymers are connected even subgraphs. Okay, and the weight is beta to the number of edges. Okay, so what's the condition here? We have some even subgraph here, and we're going to sum over all the things that are incompatible with it that are even subgraphs, anything like that. Their weight times this, let's say A is the number of edges. Now, one thing you can say is, well, how many even subgraphs of size k are there? Because with these geometric objects, there's more and more. There's many, many even subgraphs that are connected. They grow exponentially. Let's say we have max degree delta graph. Okay, so the number of connected even subgraphs is something that, let's say, touch a single vertex, so rooted, is something like c delta to the k. Okay, it grows exponentially like delta to the k. And so take that as a given. And so that sort of is what you're fighting against here. That's how many things you're summing here. And so, but the weight function is like beta to the k. And so as long as beta is less than some small constant over delta, then you're going to get convergence. Okay? So what this is saying is for this Ising model to perturb around independence, you need to take beta small. It can be positive or negative, actually. But it needs to be small. And how small does it need to be? Well, it really depends on how much interaction there is in the edges. So it scales like 1 over delta. Actually, similar scaling to the hardcore. OK, good. So that's 2 examples.
So Will, for this, so for Ising, did you get the right bounds for C on any?
No, definitely not. So that's a great question. So in particular, this is going to be much smaller than like beta critical, at least by some constant factor in any dimension. So this is a really good point. The tagline of this whole method is it's a perturbative method, which gives very precise results, but you should not expect it to work all the way to where the probability works. And one reason you can see in the hardcore already, right? Like what's stopping this convergence? It's the negative lambda, right? And so actually go back to Quiqui's talk. What was lambda for Quiqui? It was E over delta, right? Not 1 over E delta. And that's because if you specialize to the probabilistic case when lambda is positive, you have nicer behavior. Okay, but here it's really complex analysis comes in, and so you're gonna fail to converge for reasons that don't have to do with your model.
So let me ask a follow-up.
Yeah.
So I mean, for some of these things, like, you know, you can compute more than just like the partition function in real settings for like real betas, but you know, you could have multivariate and complex values. So is the best constant you get out of these types of things connected to tight thresholds of some other problem? I mean,
you mean the best thing I can say is this. It is, I mean, for the graph things, like the best constant you get is it has to do with like where zeros are on trees. But yeah, I can't say much more than that, I don't think. Okay, so these are two examples, and let me just say, once you have convergence in any of these settings, remember, go back to the start of the first lecture where we talked about moment-generating functions, characteristic functions. Now, if this condition holds and you just have a sequence of max degree delta graphs, blah, 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 you can prove that the size of the independent set satisfies a central limit theorem, a local central limit theorem. You have large deviation bounds. You have a formula as an infinite series for the expected size of the independent set, the variance. You have any information you want, as long as you're happy with numbers as infinite series. But if you like pi is an infinite series. These are infinite series. So really, once you have convergence, then you have everything. So it's great. Let me also remark. So like I said, you should think of this as n. And so if you want this to be small, you want t to be logarithmic in n. Now, a very, very crucial fact is that these clusters are connected groups of connected objects, right? So, what does a cluster look like in this Ising model example? It looks exactly like this picture. It's some complex of even subgraphs that overlap in different points. And so if you want to enumerate them, well, you can pick a vertex to start at, and you can sort of enumerate by doing a wall. Okay, I won't say the details, but you can enumerate in essentially this time. And so if you want to compute the truncation of the cluster expansion up to level t, you can compute this in time like, let's say, order n, and then maybe something like c delta to the t. Okay, and if t is like logarithmic in n, then this is like polynomial. This is like n to the log delta or something like this. So it's polynomial but with a bad exponent. But if you think of delta as constant, that's what it is. And this is, Barvanak's method has this, and then Patel and Rex, showed how to compute the coefficients in Barvanak's method efficiently using, they didn't know this about the cluster expansion, but it's exactly the same fact. Okay, so good. So for the rest of the time, I want to give two examples of applications. And yeah, they're gonna be different. One's an algorithm and one's sort of a combinatorics problem, but that has some statistical element. But one objection you could have right now is, well, I'm requiring like weak interaction, or I'm requiring very sparse independent sets. And already we saw that Markov chains are much better in either of these settings. They give you algorithms in a wider range of parameters. So why is this useful? So let's look at a different example. So we're going to look at hardcore on a bipartite graph. Okay, so my graph, I'm going to call one side L for left, one side R for right, and all the edges go across. Okay, and I'm going to make some assumptions on the graph. So assume that it has max degree delta. And I'm also going to assume that it's an expander. And so what do I mean by an expander in this setting? I mean, if you have a set of vertices that are on the left or on the right, but a set of vertices on one side, I want the number of edges going out to be large. Okay? So, and let's say the size of S is at most like n over, I don't know, 20. Okay? And we're going to assume that the size of the neighborhood of S is at least 1 plus alpha. So alpha is going to be something positive times the size of S. So you don't just get like your own self as your neighborhood. If you were a regular graph, you would always get at least your size. But we're saying you get a little bit more as long as the size of your set is not too big. So this is some bipartite notion of expander. And now what I want to do is I want to rewrite, and we're looking at, we're trying to calculate or approximate the partition function. And what I want to do is I want to do it in a kind of funny way with color. So, this goes back to also the first lecture. We had this bipartite graph, Z2, with boundary conditions. And we said if lambda is large, we expect either mostly even or mostly odd. So here we have a bipartite graph left and right. We have some nice expansion condition. We might expect on a typical sample to see mostly left occupied or mostly right occupied. And so that's what we want to study. And so what I want to know is, let's assume that we think that most left guys are occupied. I want to fix some guys on the right to be occupied. And I want to know what's the contribution to the partition function from independent sets whose intersection with the right is exactly this orange set. And let's call this set S. So in particular, I want to look at sum over independent sets so that the I intersect R is exactly S, lambda to the size of I. Okay, what is this? Well, this is, you definitely have a factor lambda for each vertex in S. And now you're thinking of this as a sparse set. If this set was empty, well, you could put every vertex in the left in or out, right? You get 1 plus lambda to the size of L. Okay? That's what you would get if there was nothing there. But you can't do that, right? Because these guys have some neighborhoods. And you can't put anyone there, right? So actually, which choices do you lose? You lose a choice, actually, for any guy in the neighborhood. So this is minus the size of the neighborhood of S. Okay. Good. So that's an identity. That's exactly the contribution from those independent sets. Okay, good. Now, one nice thing is this doesn't factorize over vertices, but it does factorize. So certainly the lambda to the S factorizes, but the 1 plus lambda to the minus neighborhood size, it factorizes over groups of vertices whose neighborhoods don't touch. Question?
Under the sum, should there be no absolute value? I mean, you're not looking at...
Oh, yeah, you're right. Good. Thank you. Yeah, it's a set. Thanks. It factorizes, and what am I going to call this kind of component? This is not a connected component here, but it's a two-linked component. It's connected in the square. It's connected by hops of distance 2. Okay, so we can rewrite this as 1 plus lambda to the size of L times the product over these two-linked components of S of lambda to the size of gamma over 1 plus lambda to the size of the neighborhood of gamma. Okay, and now for my full partition function, I can just sum over all S's. Okay, so this is an identity. Z of lambda is the sum over all X, compatible collection of two linked components of R. I'll put the 1 plus lambda to the L down here, product over gamma and X. Okay, so this is an identity for the partition function, but I've written it in terms of like these, what I think of as defects from the nice pure all left independent set. Okay, so that's good. And now, so this is exactly a polymer model partition function. You have compatibility would just be if you take the union of two polymers, they're incompatible if they are two linked, and compatible if they're not. So all good. When is this weight function small? So the weight function is small, so let's call this weight of gamma, is small if lambda is large and neighborhood of S is large compared to S. Okay. Right? If lambda is very big and then the neighborhood is much bigger than the size of the set, this is an exponentially small thing, which is good, right? That's exactly what we want for Kututsky price condition. Now, something is wrong, right? Because we started with the intuition saying, I'm either mostly left or mostly right. Let's imagine I'm mostly left and then come up with this polymer model. But then I just wrote the real partition function, and there's nothing about left or right. Okay? So we're going to change things a bit. So what we're going to do is we're going to say z left is going to be the same thing, sum over x, compatible. But we're going to insist that all polymers are of size at most n over 20. Okay? So we're just going to say that you don't have like this giant polymer that takes up all the left. Okay, and then the same thing. So let's say 1 plus lambda to the L. And then we have product of gamma and x. Okay, and then I can define the same for z right. Okay, and now comes the algorithm. So the algorithm has 3 steps. So the first step was define z left. Z right. Okay, by making polymers small. Step 2 is to show that 1 plus lambda to the L z left plus 1 plus lambda to the size of r z right is, let's say, a 1 plus or minus e to the minus constant times n approximation to z. Okay? So I've defined these 2 polymer models by saying you don't have the big polymers. And what I want to say is now, if I just add these 2 things, then I get an extremely good approximation to the real partition function. Okay, so how do you show this? So this will follow. This is actually, what you do is you prove like a slow mixing result. So what is it saying? It's saying that you have left dominated and you have right dominated, and there's something in between, and you don't want this to contribute. So that's saying that the state space has an exponentially small bottleneck. Okay, but this is just slow mixing result. So there was a question during Quiz talk like, if Glauber mixes in exponential time, can you say something about sampling? Actually here, slow mixing of Glauber really helps your algorithm. It says you can just focus on these 2 pieces. Okay, so you prove that, and then step 3 is you truncate the cluster expansion. For log z left, log z right. Okay, and then this gives you a polynomial time approximation algorithm for z. You can convert this into a sampling algorithm, and so on. But what did it rely on? It relied on taking a different perspective from the cluster expansion, now going to this third picture from the beginning, where you say, well, for large lambda or large beta, you're a perturbation of one of the optimizers. And now you're saying with cluster expansion, you can really accurately measure the perturbations from one of those ground states by making your polymer model somehow measure deviations from this ground state. Yeah.
So, but still, in terms of comparison to Markov chain, we can imagine you condition on being on one of the phases by pinning some guys. So would the picture carry through? We don't know.
Oh, you mean like, can you use this or can you prove this picture with Glauber?
Yeah, just with Glauber, like pinning some guys on the left and then pinning some guys on the right.
Yeah, or like, another way to say that is you could just start Glauber in a ground state and run it.
Yeah.
So people are starting to prove this. So the first paper I know is Alistair Sinclair and Reza Gassari. They proved this for easing. They proved it for, I think, random graphs and for like lattices. And now there's another paper with random cluster on random graphs where they use actually estimates that we did for cluster expansion to show this algorithm works. But it's a great question because this is a bad algorithm. Like it was already a pain in the butt to calculate the second term, and now we're saying calculate the log n term. Yeah, the right algorithm would say Glauber mixes slow, but start in a good place and then average them. So yeah, people are starting to prove exactly this. Good. Other questions? I'm going to move on to the other example now. So so this, and then this is like kind of a general framework where now if you have some structure to your graph, like here we had expansion, maybe you can have a lattice, you can have different types of structure, but then you can get algorithms in the strong interaction regime, which is somehow the opposite of what Markov chains do. Good. Okay, so second example is going to be something new, and we're finishing this paper. It's a combinatorics problem, but it has some algorithmic content to it. And so let me set the stage. So what I'm going to talk about is just triangle-free graphs on n vertices. So our space now is like all graphs on labeled n vertices, all triangle-free graphs. And we want to know something about the landscape, the number, sampling these things, stuff like that. So for those of you who took a combinatorics class at some point, like extremal combinatorics, often like the first extremal combinatorics result is the optimization problem. So Mantel's theorem says, which triangle-free graph on n vertices has the most edges? Okay? And the answer is, well, you can have n squared over 4 edges, and this is achieved by a complete balanced bipartite graph. Okay, so that you should keep in mind as like, think of a complete balanced bipartite graph as like the all plus easing configuration. It's the ground state. It's the max weight configuration. Okay, and now we could ask about the probability distribution. So a theorem of Erdős, Kleitman, and Rothschild says the following. Almost every triangle-free graph is bipartite. Or in other words, this is an asymptotic formula. The number of triangle-free graphs is 1 plus little o1 downstairs times the number of bipartite graphs. And bipartite graphs is easy. It's a fun exercise. You should do it, but it's easy to write down the formula. You can also think of this as a sampling statement. So the sampling statement is, if you want efficiently to sample a triangle-free graph up to total variation distance little o1, so just like Quiqui's setting, what you can do is you can just pick a random partition of your vertex set. You have to be a little bit careful. You have to calculate what the imbalance should be. It turns out the imbalance should just be constant. You pick your partition like AB. So pick AB. Now you have a partition of your vertex set. And now just include every crossing edge independently with probability half. Okay? That's a very easy sampling statement. And this theorem says that is little o1 total variation distance from uniform on triangle-free graphs, which is much more complicated.
So what happens inside the little o1? I mean, so somehow like if the little o1 were like 1 over log n or something like this, you'd hope for the sampling results that you could boost them to get lower and lower TD.
Yeah, so you can pretty accurately calculate what the little o1 is. Right. It's basically like some triangle-free graphs can arise from more than one partition.
Right.
And so basically, like, what's the probability that a graph could arise from more than one partition? It's like you need a vertex to basically be able to be put on either side. And so basically it has to have degree 0. So it's something like 2 to the minus n over 2. That's the relative error. But you can calculate this. Yeah, good question. OK, so that's nice, but you could ask for more. You could say, OK, well, that's very dense graphs, of course, like the extremal example you see. You could say, well, now you look at triangle-free graphs where you fix the number of edges, you can say, get sparser and sparser. When is this still true? So this is a paper of Ostas, Promel, and Taras. And what they found the sharp threshold where this is true. So what they said is if the number of edges is greater than 1 plus epsilon times some constant, root 3 over 4. Okay, by the end of the lecture, you'll know what is root 3 over 4. N to the 3/2 root log n. Then almost every triangle-free graph, n vertices, m edges, is bipartite. And if you do 1 minus epsilon, this is false. Okay, so this is a sharp threshold. And again, this is a sampling algorithm. So what's the sampling algorithm? You pick the partition AB, and then you pick a set of m edges uniformly at random across. OK, so what do we want to know? What we want to know is what happens when you go sparser, when m is smaller. Okay, and this is joint work with Matthew Jensen and Aditya Padakuchi, this whole framework. And here, somehow n to the 3/2 is like really something critical. And so if you're much smaller than n to the 3/2, then there's no, like, the max cut is like half the edges, and you can do some generalizations of Janssen's inequality and things like that. Whereas here, we're saying the max cut is all the edges. So what we're interested in is when m is such that the max cut is almost all the edges. Okay. So if you go below this root 3 over 4, and it's not bipartite anymore, you're going to start to have edges inside A and B. Can we characterize their distribution? Can we asymptotically enumerate? Can we sample? Okay, so that's what we're going to do. Let me switch a little bit just to make things easier. So I want to switch, and now my z of lambda, is going to be the sum over triangle-free graphs. Lambda to the size of g. So this is triangle-free graph on n vertices. Size of g just means number of edges. Okay, so this is some weighted count. Of course, this up to scaling, this is the probability that g and p is triangle-free. Okay, so I'm switching from fixing the density to fixing the prior edge probability, but it's a nice translation. The translation is basically that lambda times n squared over 4 should be like m. And so the Ostas Permoltara's threshold is lambda is root 3 square root log n over n. Okay, so this is a nice object. Does anyone know what the relation to independence polynomial is here? So it actually is an independence polynomial. It's the independence polynomial of a 3-uniform hypergraph. So the hypergraph, the vertices of the hypergraph are edges of the complete graph. Okay? So a subset of vertices is a graph. Right? It's a subset of edges of the complete graph. And what's the condition? Well, you have a hyperedge if your 3 edges form a triangle, and you're not allowed to include those 3 vertices of the hypergraph. And so it's literally the hypergraph independence polynomial. Okay, so these things really are nice. So, okay, so what are we going to do? And where does the cluster expansion come in? That's what I want to say. And this will tie into the other examples. And so hopefully you can start to make some analogies for problems you like. So step one is you want to get some rough structure. Okay. So rough structure in this example was saying that a very small fraction of the partition function comes from things that are neither left nor right. That's rough structure there. Rough structure in some other problems is, you can obtain with like a piles argument or something like this. Hypergraph containers, if you know the method of hypergraph containers, this is a method to get rough structure. So you need something with rough structure. There's a theorem of Wuchuk that says if M is at least C n to the 3/2 for large C, then there exists a partition AB so that 99% of the edges are crossing. Okay, so what I mean is with high probability over a triangle-free graph with n vertices, m edges, there's some partition that has 99%, a cut with 99% of the edges. So that's one rough structure. We start here, but we prove a little bit more. So what we prove is with high probability, there exists a cut AB so that the max degree of the subgraph induced by A and the max degree of the subgraph induced by B is at most, let's say, 1 over 20 lambda. Okay, so all we're saying is now our rough structure result is almost all triangle-free graphs from this distribution. You can find a partition so that it's going to have a lot of edges crossing, and then some, I'll call them defect edges inside. Okay. At the moment, we don't know anything about these defect edges, except the max degree inside is at most 1 over 20 lambda. In particular, as lambda goes up, this bound goes down, as you sort of would expect, and as lambda goes down, this goes up. Okay, good. And so what do we want to do? We want to think algorithmically. So let's think like an algorithm. So, and here I mean I want an algorithm to sample from this model, approximately. And what are the steps going to be? You're going to pick your partition AB. Then you're going to pick these orange edges. So pick S in A choose 2, T in B choose 2, according to the right distribution. We don't know what the right distribution is yet. That's what we need to do. And then 3, given AB and ST, pick the crossing edges. Okay. Yeah, that seems like a reasonable plan. I mean, at the moment, of course, it's correct, but we want a simpler understanding. We want to come up with something that's nice to compute that is very close to this. And so I'm going to go in reverse. I'm going to tell you how to calculate this, then that will tell you how to calculate this, that will tell you how to calculate this. So let's go in reverse. So our picture looks like this. Now we have the orange edges and we don't have the white edges. Okay, so this is very similar to what we did up here, right? You fix these right vertices and then you have the other ones going across. But what happens? If I put one orange edge in, what does that tell me about the crossing edges? Well, for every vertex here, I'm not allowed to have this pair. Okay? So actually one edge, let's say they're both size n over 2. Each edge introduces n over 2 constraints. And actually this is it. So what is the distribution of the crossing edges? So mu of crossing edges is proportional. Well, it's lambda to the crossing times the indicator that you don't violate these constraints. Don't violate. Well, these are pairwise constraints. This is exactly an independent set model. So this is the hardcore model on the graph. I'll call it S box T. So A and B are implied. But this is the graph where the vertices are A cross B, all the crossing edges. And you have an edge between them if they touch on one vertex and their other two endpoints are an orange edge. Okay, that's kind of nice. Good. And okay, so this is exactly a hardcore model. It's going to turn out actually that this condition means it's like subcritical hardcore model, so it's easy to sample from. But now we want to say, what's the probability that you pick the orange edges? Well, what's the probability you pick the orange edges? This is proportional to, well, it's lambda to the size of S plus T, right? You get a lambda for each edge. And then you have to sum over all the ways of putting in the crossing edges. Okay, great. That's the hardcore partition of S box T. Okay, so the probability you pick the orange edges is some prefactor with the number of edges, and then it's multiplied by this partition function it induces. Now, the great thing is that, okay, the max degree of this graph is actually the max degree of these. So the max degree, delta of S box T, is at most, let's say, 1 over 10 delta. Okay, but remember, what is our Katetsky price or Shearer condition? Cluster expansion converges if lambda times max degree is at most 1 over E. Well, this is great. Lambda times max degree is at most 1 over 10. Okay. So by assuming that S and T have small max degree, now this has a convergent cluster expansion. Okay, so we can write this now as proportional to, fine, lambda to the S plus T. Now this is E to the log of this partition function. I probably erased what I shouldn't have erased. You can sort of vaguely see this here. But right, this is a triangle-free graph. This crossing graph can't have triangles. To have a triangle, you would have needed an orange triangle. We know we don't have an orange triangle. Then it's minus lambda squared times the number of edges plus something about p2s times lambda cubed. Okay? So let's write that expansion. You know, I'm being very rough here, but minus lambda squared. What's the number of edges? Well, each orange edge gives n over 2 edges. Let's say the A and B are size n over 2. So n over 2 times size of S plus size of T. And then plus, let's say, lambda cubed times the number of p2s of S box T. Okay. So this is starting to look better. So I want to define Q over 1 minus Q to be lambda e to the minus lambda squared n over 2. Right? I have something here, something that factorizes that's like some number to the size of S times some number to the size of T. I'm just going to call that some number Q, Q over 1 minus Q. So this now becomes Q over 1 minus Q to the size of S, Q over 1 minus Q size of T. Okay, let me hold off writing the P2s. What would it mean if that was the distribution? What is this distribution? If the probability you pick S and T is proportional to Q over 1 minus Q to the size of S, Q over 1 minus Q to the size of T, what's that distribution? Yeah, but what names are associated with this distribution?
Call it the ideal gas. Independent ideal gas.
No, there's a nicer name that we all use. So which distribution on graphs is proportional to q over 1 minus q to the number of edges? Erdős-Rényi. Okay, this is the Erdős-Rényi graph. So if that was it, we would be saying that actually these orange edges are exactly Erdős-Rényi edges with q. And notice, look at q. Q is funny, right? It's like lambda. That's the overall edge density. But you get this really big penalty too. Okay? And so what is root 3? What's special about root 3? This is exactly when this q crosses 1 over n squared. And so if you have Erdős-Rényi random graph with an edge probability that's much less than 1 over n squared, almost surely empty. That's Ostas Permaltaras. But now like as the constant in front changes, as it goes down, the constant in the exponent of q goes up. So you start to get more and more and more edges. Okay, so good. But you still have to deal with this, right? There's this, okay, and I didn't even say how to deal with the higher order terms, because this is really an infinite expansion. So assume that we threw away that stuff. You still have e to the lambda cubed p2 of s box t. Now I have to remember what it is. Good. So I'll write this formula. You can check this for yourself. So what I'm asking here is, in this funny graph that you construct with the crossing edges, how many P2s are there? Notice you get a P2 for every edge and every vertex. Is that right? No. Is that what I want to say? No, sorry. What is a P2? A P2 looks like that, right? That's a P2 in this crossing graph, right? Because this is a vertex joined to a vertex. I need an orange edge there. Joined to a vertex. That's a P2. How else can you get a P2? If you have a P2 here, then you can get this P2, right? Okay, so there's some way to calculate this. Let me tell you what it is. It's like n over 2 P2 of S plus n over 2 P2 of T plus 4 size of S times size of T. Right? That's from this kind of P2. Okay, okay, now we have something else here, and I'm going to call it e to the psi P2 of S plus psi P2 of T. Okay, just for simplicity, I'm going to ignore this cross term. You do have to deal with the cross term. But let's even just look at this. Okay, so now I won't put everyone on the spot, but Guy, what kind of distribution is this?
This is my favorite distribution.
I know.
Yeah, it's an exponential.
Good. So this is an exponential random graph, right? This factorizes, and so now you have this Erdős-Rényi thing, but then you have an exponential, and psi is like lambda squared, lambda cubed, n over 2. So it's something like 1 over root n, and then some very weak favoring of P2s. Okay, so you could say, oh, great, that's amazing. This distribution is just an exponential random graph. So that's false. So if you pick a sample from this exponential random graph, actually the model blows up. The P2s, even such a weak favoring of P2s, makes the edge probability be way, way bigger than Q. Okay, you blow up. You basically, the model wants to like shift to a different partition. Okay? And so instead what you need to show is that the distribution is close to something else. So then what you want to say is mu of ST is proportional to Q over 1 minus Q size of S, Q over 1 minus Q T, e to the psi P2 of S, e to the psi P2 of T. But then you need to put an indicator function that delta of S, delta of T is at most 1 over 20. Okay. Because that's you started with that assumption that you had bounded max degree. And this actually really skews the distribution. You go from an exponential random graph that's going to blow up and be really, really far from the Erdős-Rényi random graph and completely ruin your assumption, to once you put in the conditioning, it really stays close to something looking like Erdős-Rényi. Okay? And so this, at least in some regime, for some constant, like I think lambda bigger than 1, we show that this is the true distribution. Okay, but you can go further, and maybe this is the point I wanted to bring to this audience. Now what you're interested, you could ask, is this thing actually doing something? So this is like 1 over root n times the number of p2s. So if you're really, really sparse in this Erdős-Rényi random graph, and you have like n to the 1/10 edges, the number of p2s is going to be tiny, right? And so you're not going to notice it at all. So really, in some regime, you could just ignore that, and you'd be fine. At some point, you'll start to notice it, okay? But you'll start to notice it in like the normalizing constant first. So this will behave like a constant. Okay, so it will change the asymptotic count, but basically, with high probability, the p2 thing will be concentrated, and so then you can show that the KL divergence with Erdős-Rényi is small, goes to 0. But then at some point, these actually do start to matter. And so one thing, by sort of like using the cumulants, we can like very accurately study the KL divergence between the true model, so mu st, the Erdős-Rényi GNQ model, the conditioned ERG, and there's some point at which it becomes singular to Erdős-Rényi, and the p2s actually matter. It's actually exactly the point where giant components emerge inside the pieces. Yeah. So.
It seems a little bit ad hoc to put this indicator. I mean, except for the fact that you have this lemma, but you proved the lemma. So I mean, someone who's just trying to turn the crank on this method, like, what are they going to? How do they get that? How do they get this?
Yeah. So I mean, that's a really good question, and we could discuss for a long time. So in some sense, you want to maintain the rough structure, right? And you want to do it in somehow the simplest way possible. Max degree condition is really is like very nice for cluster expansion. You could say, well, the number of edges is not too much larger than it should be. But that like doesn't quite let you get the cluster expansion, because cluster expansion is very sensitive to even local changes. So basically, I mean, there's nothing special about 1 over 20. Sure. Like you just need to keep it away from the blow-up point. And so I think there's many, many things you could put in as the rough structure, but you need something. Otherwise, you blow up. But it's a very good question.
Okay, so there's some flexibility.
Yeah. But you need to make sure that you stay in the world that you meant to stay in, where you have this partition as your nice thing. Okay, so let me conclude with a couple just philosophical remarks to try to like encourage you to think about this. So let's say you're interested in like statistical problems where you're trying to distinguish probability distributions, like block model from Erdős-Rényi or random geometric graph from Erdős-Rényi. Oftentimes there's some like local statistic, like some count of small subgraph that is a nice statistic for distinguishing, and it works here, doesn't work here. Somehow you could imagine that like the KL divergence has a nice convergent expansion in terms of like something like cluster expansion. What is the cluster expansion? It's a series with subgraph counts where the smallest subgraphs count the most, and then there's exponential decay. And so I somehow think that if you have a statistical problem where you know that a decent distinguisher is some small subgraph count, there should be some expansion there. And the expansion, using some nice machinery, maybe you can show as a convergent infinite series, and then maybe you can really finally find statistical thresholds. The other thing I would say is like, notice what's happening. You're starting with rough structure, and you're using this machinery to get very precise results. And precise meaning like 1 plus little o1 downstairs, or little o1 total variation distance. So there's lots and lots of problems in math and computer science where you get 1 plus little o1 in an exponent. That's rough structure. So this method should be able to bring that 1 plus little o1 downstairs and get also total variation distance results. Because you need to know some rough structure. It's not like a free method. But if you know rough structure, then you can hope to apply this. So I would be very interested to hear if you guys have applications or things like that. So definitely contact me or ask questions. I'd be happy to hear. But that's it.